This next theorem here is dealing with the volume of something underneath a two-variable function. So if we have f of xy, that's a function with two variables, that's continuous over the rectangular region we're going to define as R, which again shows a two-variable function xy in R2. Or we have some value x that's between real numbers a and b, and some value y that's between real numbers c and d, then what we get is the double integral of f that equals the integral above, and the picture of it looks like this. So if we do it by a, we look at the area of each x, or at least the area of the each slice with respect to x. And if we do it with b, we look at the y's first and go across with the y's. We're going to get the same thing. Doesn't matter which way you do it. Just make sure that you pair up. So I've got the c's and d's. CD has to go with the dy, and the AB has to go with the dx. And again, the order that you do it doesn't matter. Just make sure that you pair up the dx with a and b and so forth. So if you do dx first, just make sure you evaluate it at AB first. They give you a note here that if it's discontinuous and only a finite number of curves, it'll work. Basically, as long as f is integrable over R, you're going to be fine. So let's try to do this problem here. All right, so it doesn't specify what order we're supposed to do this in, so I'm just going to leave alone. So I'm going to draw a little bracket around this. We'll be doing the inside first. So that cosine of 3y, because we're dealing with dx, is just going to be a constant, so we can pull that out. However, sine of 2x, the integral of sine is negative cosine, but we have a situation where we don't have u specifically, so let's make a quick substitution. So if we let u equal 2x, then du equals 2 dx, which means that du over 2 equals dx. So we have to have a 1/2 in there. So this is going to equal. So I'm going to pull out the cosine 3y. And we have the 1/2, so we'll put the 2 there. And this is going to be sine of u. All right, so again, the integral of sine of u is negative cosine. We'll replace the u. You know what? Let's do this, and we'll put the dy on the outside. Okay. Sorry, we have to evaluate that from 0 to pi by 2. That's what we want to do. And the dx is gone because we just did it. Sorry about that, but again, this is fine. All right, so we need to evaluate that at pi by 2. We just plug in pi by 2 where we see x. So this equals it's negative cosine 2x. So 2 times pi by 2 is just going to be pi. And that's going to be minus cosine of 3y over 2 times negative cosine of 0. And then let's make another bigger bracket, I guess. And we'll do dy. All right, so this should clean up pretty quickly and easily. Cosine of cosine of pi is going to be -1. So this is going to be -1 times -1 is 1. So it's just cosine of 3y over 2. And cosine of 0 is 1. So this is going to be minus a minus cosine 3y over 2. So this looks like just cosine of 3y. I've got 2 of them, and then the 2's will cancel. I guess I don't need this bracket here. All right, so I'm not going to take the integral. Again, we're going to need, let's make a u substitution here. Let's make it a v. I made a u earlier, so let's change it to a v. So v is 3y, which means dv is equal to 3 dy, which means that dv over 3 is equal to dy. So I need a 1/3 in front of this, so this is going to equal 1/3 integral of cosine of u du. Integral of cosine is just sine. So this is equal to 1/3 times sine, and our u is 3y. We're valuing that from 0 to pi. Well, this gives us 1/3 sine of 3 pi minus 1/3 sine of 0. But that's just 0 minus 0, which is 0. 3 pi is essentially pi. It's coterminal to pi, and sine is 0 at 0, pi, 2 pi, 3 pi, and so forth.